Hi, I'm Ben-Yaakov. This presentation is entitled What Made the LM324 Revolutionary? Now, the LM324 operational amplifier family was actually introduced by National Semiconductor in 1972. The company actually was bought by Texas Instruments in 2011, I guess. Its main innovation of the LM324 was the ability to operate from a single low-voltage power supply. The single supply operation was quickly adopted by the industry and is now the most favored approach. The 324 family and its variants are still being used today extensively, almost 50 years after it was first introduced. This operational amplifier are now offered by many manufacturers, and there are some different variants of this unit. Now, this presentation explains the innovation steps taken in the design of the original LM324 family to achieve single supply operation and a minimum voltage of about 0 volt at the input and output, which is important for single supply operation. Now, the precursor of the 324 was the LM741, which was introduced by Fairchild in 1968. This is the inner circuit of the LM741, which was also innovative in its time because of the fact that it was the first operational amplifier, as I recall, that included the compensation capacitor within the unit rather than having two pins for compensation. Now, the LM741 was intended to operate from a dual supply, plus and minus, and the ground in between. And it needs a dual supply because of the fact that you have here a differential amplifier, and then you have quite a bit of a circuitry here, which I'm not going into, and therefore you need some voltage between the common mode at the input and the negative rail here. So therefore, if you try to operate the operational amplifier with a common mode at the input, which is the negative supply, as is the case of a single supply, it will not work because these transistors are not biased. So let's have a look at it here closely. What I'm saying is that if you have a differential amplifier and you have a circuit here, in fact, even if you don't have it, and this is actually connected here, then if this common mode now is tied or same potential as this negative rail here, then there is no voltage to actually bring this transistor into any linear operating region, and therefore this cannot work. So therefore, for the LM741 and all the other amplifiers at that time, you'd need a dual supply. The ground was somewhere in between, usually in the middle, like plus 15, minus 15. And then, of course, you can have a swing around the ground. So the LM324 was to solve this problem. And the key factors required to solve the problem is that you are able to get a common mode close to ground or the negative rail, you might say. And at the output, you also would like to get as close as possible to ground. So you know you want common mode here at the input close to 0 and output which is going very close to ground. However, one has to take into account that there are, of course, limitations to the single supply. For example, the output cannot be negative voltage. That is, if you have a positive supply, the output can be only positive. Therefore, in the case of a non-inverting amplifier, the input has to be 0 or higher. And in the case of an inverting amplifier, the input has to be lower than 0, that is negative voltage. Now, there is a possibility to operate a plus-minus or a dual supply operational amplifier with a single supply. I'm showing it here. Suppose you have a supply between here, VCC to ground. You generate a midpoint. You bias the amplifier to the midpoint. You feed the signal through a capacitor, and then at the output through a capacitor, and here you have like a single supply, but this is not really a single supply. It's an offset, and then you operate around this artificial, you might say, midpoint. Obviously, this is not possible for DC, only for AC, and limited by the size of this capacitor. So we are not talking about it. We are talking about a real single supply operation. So the LM324 was designed in a classical way with 3 stages. There is an input stage differential amplifier, the intermediate stage, and there is an output amplifier for providing the current at a higher level. The actual circuit has here actually a GM amplifier, that is voltage to current, and here we have a Miller capacitor, which is sort of generating a low frequency pole needed for compensation, and I'll talk about it a little bit later. So here is the circuit or simplified circuit diagram of the LM34. We have the input, intermediate, and output. You can see it here. This is the input stage, the differential amplifier. This is the intermediate stage. This is the compensating capacitor built in. And then we have the output. It's actually a push-pull, complementary BJT transistor push-pull to get the relatively higher current at the output. So let's have a look first of all at the input stage, the differential stage. It's a bit different from what we sort of think about a differential stage. First of all, it's sort of upside down here. We see that these are PNP transistors. The emitter is up and the collector is down. And then we have here, we'll see it in a minute, a current mirror. So what's the reason for this thing? And this is the key point here, which makes possible the common mode to be close to ground. So let's have a look now at the differential amplifier from the point of view of biasing. Let's start off with this current mirror. We have a transistor here which is connected as a diode, and then the base is connected to this parallel transistor. This is a current mirror because if we are pushing current here, then the base voltage, which will be adjusted here according to this current, this is like a diode, so the voltage here will be a function of the current. This same voltage is now fed to this transistor, and if these are the same, then of course with the same GM, then we'll have the same current here. The point is that a transistor which looks connected like this, which is a diode as I've said, is in fact inside in the linear mode. This perhaps contradicts intuition, but this is the fact. So what I'm saying is that if you have a transistor which is connected such that you have, say, 0.6 volt here and 0.6 volt here, it is still in the linear region. Why is that? Because if we look at the Eber-Small model, here it is, we have 2 diodes, then we have 2 current sources which are a function of the current through these diodes. Now, if the base to emitter diode is conducting, we activate this current source, and if this diode is non-conducting, then this source is 0. Then therefore, in this situation, we are in the linear region. That is, the definition of the linear region is that we have this diode conducting and this diode non-conducting. Now, if the voltage of the collector and the base are the same, if the voltages are the same, 0.6 in our case, then the difference is 0, the diode does not conduct. So the transistor is still in the linear region, which is okay. So we understand now that this current source is now biased at a linear operating point. Now the question is, what about the signal that we need here? Now the bias point is awfully low, like 0.6 volt. And obviously when the operational amplifier is operating, then we need to pass some AC, and therefore we're going to have a AC superimposed here, and it'll be quite limited. But that's okay, because we have here an intermediate amplifier which is amplifying this signal to whatever is needed at the output. Say you might need at the output like say 10, 15 volt, and for that you need this say 10 volt divided by the gain here, and this is the AC that you'll see here, which could be very small, like 0.1 probably will do the job. So there is no problem here, but let's have a look now at this stage here. Now what about the common mode here? We see here now that we can connect the input to the ground. Obviously the physical operational amplifier, you don't want to tie these two together because of offset voltages, but as a mental experiment here we just connect them together and to ground. So what happens now with this stage? Here is 0, here is 0.6, and here is 1.2 if I take it 0.6, and here is 0.6 because of this. So this transistor has on it 0.6, this transistor has on it 0.6, so these transistors are also in the linear region. So by having this current mirror and flipping over the differential amplifier, we can obtain here proper biasing to all the transistors and ability, of course, to connect the input or having a common mode at the input, which is 0 volts, which is, of course, the absolute necessity for operating with a single supply. Now we have here actually now two transistors, which kind of in a Darlington configuration, and by this we can get a fairly low input bias current with fairly low beta. For example, if the beta is say 10 and we have two transistors, then if we have here 6 microamp, this is actually 6 not 5, then the input bias current will be this value over the total current gain, so it will be 50 nanoamp, which is of course very nice. So what about the intermediate amplifier? We have here actually a follower. Okay, this is a high impedance, so we go out at the emitter, and then we have a Darlington here. As a matter of fact, there is some resistor here in parallel to this base. So this is like a common emitter stage, and the output goes from here to this push-pull stage. Okay, and then we have this feedback through this capacitor, which is a Miller capacitor, and as we know, this Miller capacitor, or this capacitor across an inverting amplifier, is reflected to the input as this the actual value times 1 plus A being the gain. So therefore we get an effective large capacitance, although this is relatively small because of the monolithic technology will not allow large capacitors because it takes a lot of area. So by this arrangement we get a large capacitance, and with the impedance involved, okay, the impedance here, we get the pole which is actually shaping the overall gain of this amplifier by having a pole at a fairly low frequency. So by this, rather than having a open loop gain that looks like this blue one, which has many poles here and therefore quite a bit of a phase shift, and the phase margin will be very bad when you operate it in a gain of 1. Then by having this dominant pole at a very low frequency, we get almost a 20 dB per decade, so therefore the crossover will be perhaps 90 degree plus, well actually there is another pole here in this vicinity which I'm not showing, so phase margin will be pretty good. So here it is, this is from the datasheet. We see the overall gain, open loop gain, and we see that we have a pole at around between 1 and 10 hertz depending on the operating condition, and then it goes 20 dB per decade and a unity gain bandwidth of 1 megahertz, which is kind of very typical of these types of amplifiers even today. Now what about the output amplifier? Well, here we see the push-pull, we see here a Darlington again, and then we have another unit here. Let's have a look at it closer. We see here another unit. This is the push-pull. We have here two transistors, and there's one transistor here. I'll talk about it in a second. So, what are the sinking and sourcing capability of this unit? As far as the sourcing goes, we have here a source of 100 microamp, and then there is a Darlington. So 100 microamp times beta of this transistor times beta of this transistor is about the current we are going to get here. What about sinking? Well, so the best this unit can do is to have this transistor sort of saturated. And in this case, we are sinking this current. But then, of course, the question is, what is the drive of this transistor? Because the maximum current that we can have here will be the, let's have a look at it here, will be the base current times beta of this transistor. Okay, this is the path here. So therefore, by having a specific source here, which is determining this current here, this will eventually determine what is the current of the base here, and therefore what is the output sinking capability, which so is adjusted to be in the range of 30-40 milliamp. Now what about the voltage levels? If we look at the sourcing condition, the best we can do will be the VCC minus 2 VBE. So it's about VCC minus 1.4, because we are fed from here. There are two base to emitter voltages, so this will be the maximum voltage. We cannot go higher than that. Okay. There is another feature here, which let me talk about it for a second. Because we have here 100 microamp times beta of this one and beta, actually beta plus 1, and beta plus 1 of this one, then we might have a very high current. So in order to limit the current, there is a short current protection. Here it is. And what it does is the following. Once the current builds up here, this is the output current, to a level which is starting to cause Q7 to conduct, that is about 0.7 volt, then the Q7 is actually bypassing the base of Q5 here, bypassing this current to the output. Now this current is a small current, so therefore the maximum output current that you can have in the sourcing will be the dependent on say the VBE, when the transistor starts to conduct, divided by this resistor, so you can adjust the output. Now for the sinking, there is no protection, because as it turns out, the design is such, let me go back here, that the current that you can get here from the preceding stage is such that the actual sinking is limited by the nature of the magnitude of the sources here. So there is no need for an extra short circuit protection. Now the sourcing behavior is shown here, and here we see now the total operation. We see here this is the deviation from VCC, or from positive rail. We see here that if we are sourcing a small current, then we are pretty close, this VBE, while there is very little current, and then it will go up to up and up until the short circuit protection starts to operate, which limits the current to be about, shown here, this is 10, 20, 35 milliamp. Okay, so this is now, this straight line is due to the fact that you have a short circuit, so once you are trying to pass a higher current, it will limit it to this value. So now the question is, what is the minimum voltage at the output? And this is very important, because this will determine the quality of this operational amplifier when operating from a single supply. You want this voltage to be as close to 0, because say you like to feed from here maybe even some digital circuit, and therefore you like it to be very close to zero. So if we look at this circuit now, we see here that the best you can do is when this is short, say, so this again is like a diode. So as you feed in current, like the amplifier is trying to push the voltage to ground, so it'll short it out, and then what you are left with is a diode, and so therefore you're going to get like 0.6, 0.7 volt here. But this is not good enough, the 0.7 volt or 0.6 volt. So what was done is to add this current source here, which is doing the trick of actually pulling the output closer to ground. This current source will also be a current mirror. So we are pushing a 50 microamp into one side, and here we're going to have this transistor which is connected to the output. So this source operates all the time. Suppose we are thinking now a small current, let's say 10 microamp, let's say we are connected here to a MOSFET digital circuit, okay? That doesn't take any current and doesn't need any sinking current. Now, if we are at that situation, we have the following. We have here a current going into this diode. We have a voltage here which is sufficient to sustain this 50 microamp. But on this side, we have this voltage, but almost an open circuit here. That is, the current here is lower than this 50 microamp. In this case, this transistor is in saturation, okay? And therefore, the voltage across it will be very low. As we push here more and more current, that is, as the sinking current is going up and up, this voltage will start going up, and eventually it will, of course, get to a voltage which is similar to this voltage here, and in fact we are going to have also the clamping of this diode, because for the case of a very low sink current, this transistor actually doesn't work. This is affecting the voltage of the output by this transistor being in saturation. And here is a summary of what is happening from the data sheet. We see the voltage here, we see the sink current. So for very low current, as I've said, this current mirror transistor is in saturation. Therefore the voltage on it, this is the voltage, is very small. As the current starts to go up, this is in milliamp. So here we are at say 10 microamp. It's 50 millivolt. And then as we go to 50 microamp, which is the magnitude of this current, then this starts to operate as a real current source, and the voltage will be determined by the push-pull transistor, that is, by this transistor. So it will be clamped to say 0.6, 0.7 volt. So what we see here is that the output can get indeed very close to zero if the requirement for sinking is of a very low current, up to 10, 20 microamp. If the required sinking current is larger, then it will jump to this 0.6, 0.7. So what can be done? Well, one way is to put a resistor here, which is also helping to lower the potential here. For example, if you put here a 100 ohm resistor, then 1 milliamp will give you 0.1 volt. But of course, if the situation is the output has to be high, then this resistor will be bleeding a lot of current. So this is not a good solution, although sometimes say 1 kilo ohm is a value that is sort of implemented. So what made possible a single supply operation? Primarily the fact that the common mode input could go very close to zero. The situation at the output is not very good. For very low currents, it's 0 volt. For a higher sinking current, it's 0.7 volt or 0.6 volt. And then at the high side, we are limited by the 2 drops VBE, so it's VCC minus 1.4. This is about the swing that you can get at the input at the output. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.